Imagine waking up tomorrow and discovering that somewhere in the universe there exists another version of everything you know, not made of matter, but of something eerily opposite. A world where particles carry reverse charges, where contact with our world would release unimaginable energy, and where existence itself seems to question why anything exists at all. This is not science fiction. This is antimatter. And the strange part is not that antimatter exists. The real mystery, the one that fascinated physicists like Richard Feynman, is why it exists at all, because according to the laws of physics, antimatter should never have allowed us to exist. The puzzle that shouldn't exist. Let's begin with something simple. Everything around you, the air, your body, your screen, is made of atoms. Atoms are made of particles, electrons, protons, and neutrons. For centuries, scientists believed these were the fundamental building blocks of reality. Then the 20th century arrived, and physics shattered that comfortable picture. When scientists began exploring the quantum world, they discovered something shocking. The equations describing particles didn't just allow for matter. They demanded the existence of mirror versions of matter. These mirrors had the same mass but opposite charge. An electron, for example, has negative charge. Its mirror counterpart, the positron, has positive charge. Same mass, same behavior, opposite identity. This wasn't speculation in 1928. Physicist Paul Dirac wrote down an equation combining quantum mechanics and Einstein's relativity. The math worked beautifully except for one disturbing detail. The equation predicted particles that no one had ever seen. Dirac didn't invent antimatter because he wanted to. The mathematics forced him to accept it, and a few years later experiments proved him right. Antimatter was real. Feynman's radical way of seeing reality. Richard Feynman loved questions that seemed simple, but hid deep mysteries, and antimatter was one of them. Instead of asking, why does antimatter exist? Feynman asked something stranger. What if antimatter is just matter seen differently? Feynman introduced an idea that still feels mind-bending today. In his interpretation of quantum physics, an antimatter particle could be thought of as a normal particle moving backward in time. Yes, backward in time. Now, this doesn't mean antimatter literally travels into the past like a science fiction movie. Rather, the mathematics describing particles works equally well if you interpret certain solutions as particles moving backward through time in Feynman diagrams, the visual language physicists use to describe particle interaction. An electron moving forward in time looks mathematically identical to a positron moving backward. To Feynman, this wasn't just a trick of math. It hinted that reality might be far stranger than our everyday intuition allows. The universe, at its deepest level, might not distinguish between forward and backward the way we do. Creation from nothing. Here's where things become truly unsettling. According to modern physics, particles and antiparticles can appear out of pure energy. When enough energy is concentrated in a small region, a particle-antiparticle pair can suddenly emerge. An electron and a positron appear together. Why together? Because nature seems obsessed with balance. Charge must be conserved. Energy must be conserved. The universe doesn't allow something to come from nothing without keeping the books balanced. So whenever matter appears, antimatter appears with it. Two opposites born at the same moment. But this leads to a terrifying implication. If matter and antimatter were created equally during the birth of the universe, and our best theories say they were, then they should have annihilated each other completely. Matter meets antimatter and both vanish in a burst of energy. No galaxies, no stars, no planets. No you, just radiation. And yet here we are. The greatest cosmic imbalance. This is one of the biggest unsolved mysteries in physics. Somehow, in the earliest moments after the Big Bang, matter gained a tiny advantage. For every billion antimatter particles, there were about 1,000,000,001 matter particles. That tiny imbalance changed everything. When matter and antimatter destroyed each other, that single extra particle remained. Those leftovers eventually formed every structure in the universe. Every atom in your body exists because of that small asymmetry. Feynman found this deeply fascinating because it challenges our assumptions about symmetry. Physics equations often appear perfectly balanced, elegant, and symmetrical, but reality itself is slightly biased. The universe somehow chose matter, or perhaps more accurately, something broke the symmetry, and we still don't fully know why. Antimatter and the nature of reality. Feynman warned against thinking of particles as tiny solid objects. In quantum theory, particles behave more like processes than things. They appear, interact, transform, and disappear. Antimatter reinforces this idea. It suggests that what we call matter may not be fundamentally special at all. Matter and antimatter are two expressions of the same underlying reality, two solutions to the same equation, like positive and negative numbers, or north and south poles of a magnet. You cannot have one without the possibility of the other. This changes the question entirely. Instead of asking why antimatter exists, we might need to ask why anything exists rather than perfect cancellation. Why didn't the universe end in symmetry? Why is there something instead of nothing? The first crack in our intuition, Feynman, once said that if you think you understand quantum mechanics, you don't understand quantum mechanics. Antimatter is one of the reasons why. It tells us that reality is not built according to human intuition. Time may not flow the way we think. Opposites may be inseparable. Existence itself may arise from delicate imbalances written into the fabric of physics. And perhaps most unsettling of all, the universe may not care whether it contains matter or antimatter at all. From the perspective of the equations, both are equally valid. The difference between existence and non-existence may have come down to a tiny fluctuation in the earliest moments of time. A cosmic accident, or a deeper rule we have yet to discover. Time feels obvious. It moves forward. The past is gone. The future hasn't happened yet. Causes come before effects. Broken glasses never reassemble themselves. Smoke never returns to the cigarette. We experience time as a one-way street. But when physicists began examining the laws governing the smallest particles in the universe, something deeply uncomfortable appeared. At the fundamental level, the equations of physics don't seem to care which direction time moves. And this is where Feynman's view of antimatter becomes truly unsettling. The symmetry hidden in physics in everyday life. Time has direction because of entropy. The tendency of systems to move from order to disorder. Ice melts. Buildings decay. Memories form about the past, not the future. But the microscopic laws governing particles don't contain this arrow of time. If you film two electrons interacting and play the film backward, the interaction still obeys the same physical law. Nothing breaks nature. At its deepest level, seems indifferent to past and future. This realization puzzled physicists. If the laws are symmetric in time, why do we experience time moving only forward? Feynman realized that antimatter might be hinting at an answer, or at least revealing how strange reality truly is. The backward. Time interpretation in the 1940s. Feynman developed a new way to visualize particle interactions. Today we call these visual tools Feynman diagrams. They allow physicists to represent complicated quantum processes with simple lines and points. In these diagrams, time usually moves upward. A particle traveling forward in time is represented by a line moving upward. But something remarkable happens mathematically. A particle traveling backward in time looks exactly like its antiparticle moving forward. An electron moving backward through time behaves identically to a positron moving forward. The equations don't distinguish between the two descriptions. This led Feynman to a bold interpretation. Antimatter could be understood as matter moving backward in time. Now, this idea doesn't mean antimatter literally travels into yesterday. You can't send antimatter messages to the past. But mathematically, this interpretation works perfectly. It suggests that what we call particles may simply be different perspectives on deeper processes unfolding in spacetime. In other words, antimatter challenges the idea that time itself is fundamental. One electron. Many histories. Feynman once joked about a strange possibility. What if all electrons in the universe were actually the same electron, moving back and forth through time? It sounds absurd, but the idea reveals something profound. All electrons are identical, perfectly identical. No distinguishing features. You cannot label one electron and track it forever. Quantum mechanics treats them as fundamentally indistinguishable. Feynman's playful idea highlighted a deeper truth at the quantum level. Identity itself becomes blurry. Particles are not individual objects in the classical sense. They are excitations of fields, temporary patterns in an underlying structure. Antimatter fits naturally into this picture. Instead of separate kinds of stuff, matter and antimatter may simply represent different directions of the same process. Reality becomes less like a collection of objects and more like a network of events. Annihilation, the disappearance that isn't when matter meets antimatter, both disappear in a flash of energy. This process is called annihilation, and it sounds final, as if existence itself has been erased. But from the perspective of physics, Nothing truly vanishes. Mass becomes energy. Energy becomes radiation. The total balance remains intact. Feynman emphasized this idea repeatedly. Nature conserves its bookkeeping perfectly. What looks like destruction is actually transformation. And here's the strange implication. If an electron moving forward in time meets an electron moving backward in time, the interaction can be seen as a continuous process rather than a sudden ending. The story doesn't stop, it simply changes direction. This interpretation blurs the line between creation and destruction. Particles appearing from energy, particles disappearing into energy, these are not separate events, but parts of the same ongoing process. Existence becomes cyclical rather than linear time. Causality and human intuition. Why does this feel so strange? Because human intuition evolved in a world of large objects and irreversible processes. We experience time through memory and change, not through quantum symmetry. At the quantum level, causality becomes more subtle. Events are described by probabilities, not certainties. The future influences the present through allowed possibilities, while the past constrains outcomes through conservation laws. Antimatter exposes this tension between intuition and reality. If the equations allow time symmetry, then our experience of time's direction may not be a fundamental feature of the universe. It may emerge from statistical behavior at large scales. The arrow of time could be a consequence of complexity, not a basic rule. And that means the universe at its core might be far less directional than we imagine. The universe without preference, one of the most shocking implications of Feynman's view, is that the universe itself might not prefer matter over antimatter, or past over future. The preference we observe could arise from initial conditions, the specific way the universe began, rather than from the laws themselves. Imagine flipping a perfectly fair coin at the beginning of time. Once it lands, history unfolds from that outcome. But the laws governing the flip were always neutral. Similarly, antimatter suggests that existence itself might be balanced at a deeper level, even if our local universe appears biased. This idea reshapes the question. Instead of asking why antimatter exists, we begin asking why time flows the way it does for us, and whether that flow is simply a local illusion within a larger, timeless framework. The edge of understanding Feynman often reminded students that physics doesn't explain why nature behaves the way it does. It describes how it behaves with extraordinary precision. Antimatter sits at the edge of that understanding. It works perfectly within our equations, yet it challenges our deepest assumptions about identity, time, and existence itself. If antimatter can be interpreted as matter moving backward in time, then reality may be less like a story unfolding and more like a complete structure, where past, present, and future coexist within the geometry of space-time. And we, moving through it, experience only one direction. If antimatter exists as naturally as matter, if the laws of physics treat them almost perfectly equally, then the universe should never have survived its own birth. This is not exaggeration. According to our best understanding of the Big Bang, the early universe was unimaginably hot and dense, filled with pure energy. As the universe expanded and cooled, that energy transformed into particles, and every time matter appeared, antimatter should have appeared with it. Perfect symmetry, perfect balance, and perfect annihilation. Yet something went wrong, or perhaps something went right, because if symmetry had remained perfect, the universe would have ended seconds after it began, the universe that shouldn't exist. Let's rewind time to the first fraction of a second. After the Big Bang, temperatures were trillions of degrees. Particles and antiparticles were constantly forming and destroying each other. Electrons met positrons, quarks met antiquarks. Energy turned into matter, and matter turned back into energy in an endless cycle. At that stage, the universe didn't look like space filled with objects. It looked more like a storm of interactions, a chaotic ocean where existence itself flickered in and out. And then something subtle happened as the universe expanded. Temperatures dropped, particle creation slowed. Annihilation continued. Matter and antimatter pairs destroyed each other in enormous numbers. If equal amounts existed, everything should have vanished into radiation. But it didn't. For roughly every billion antimatter particles, there was one extra matter particle. Just one. That tiny excess, 1 part in a billion, survived the annihilation era. And from those survivors came every galaxy, every star, every planet, and every living being, including you. This imbalance is so small that it almost feels accidental, yet its consequences are infinite. The symmetry that broke physicists call this mystery baryon asymmetry, the imbalance between matter and antimatter in the observable universe. And it raises one of the deepest questions in science. Why did symmetry break? The laws of physics appear highly symmetrical. Swap positive charge for negative, left for right, matter for antimatter. The equations mostly remain the same. Feynman found this deeply intriguing because it suggested that the universe's fundamental laws might be more symmetrical than reality itself. In other words, the rules are balanced, but the outcome is not. Imagine a perfectly balanced pencil standing on its tip. The laws governing it are symmetrical. It could fall in any direction. But once it falls, symmetry is broken. One direction becomes real. All others remain possibilities. The early universe may have behaved in a similar way. Something nudged the balance slightly toward matter, and that tiny tilt shaped cosmic history forever. CP violation. Nature's tiny bias in the 1960s. Physicists discovered something shocking while studying subatomic particles called gayons. Certain reactions involving particles and antiparticles did not behave as perfect mirror images of each other. Nature, it turned out, has a slight preference. This phenomenon is called CP violation, a violation of charge and parity symmetry. In simple terms, it means that matter and antimatter don't always follow identical rules. The difference is extremely small, almost negligible, but in the early universe. Even a tiny difference could have been enough to create the imbalance we observe today. Feynman appreciated discoveries like this because they revealed an important lesson. Reality doesn't always follow our aesthetic expectations. Physicists often expect symmetry because symmetry feels beautiful and simple, but nature is under no obligation to be perfectly elegant. Sometimes, imperfection creates existence. Why didn't everything cancel out? Here's where the mystery deepens. Even with CP violation, our current theories cannot fully explain the amount of matter we see. The imbalance predicted by known physics is too small. Something is missing. There may be unknown particles or forces that existed in the early universe. There may be processes we haven't discovered yet. Some theories suggest that heavy particles decayed in ways that favored matter. Others propose entirely new physics beyond the standard model. The uncomfortable truth is this: we don't yet know why the universe contains more matter than antimatter, and that ignorance sits at the heart of modern physics. Feynman famously embraced this uncertainty. He argued that science progresses not by pretending to know answers, but by honestly confronting what we don't understand. Antimatter remains one of those unanswered questions, a reminder that our picture of reality is incomplete. The fragility of existence, consider what this means on a personal level. Every atom in your body exists because of a tiny imbalance that occurred nearly 14 billion years ago. If the numbers had been slightly different, even by a fraction, stars might never have formed, chemistry might never have existed, life would be impossible. Existence itself depends on asymmetry. Perfect balance would have meant perfect emptiness. This idea overturns a deep human assumption that order and symmetry are necessary for existence. In reality, it may be imbalanced. Small imperfections that allow complexity to emerge. The universe exists not because it is perfectly balanced, but because it is slightly unbalanced. Feynman's perspective, accepting mystery Feynman, resisted philosophical conclusions that went beyond evidence. He didn't claim antimatter revealed cosmic purpose or hidden meaning. Instead, he emphasized wonder. The universe is understandable enough for us to describe its laws, yet strange enough to continually surprise us. Antimatter is one of those surprises, something that seems impossible at first, yet fits perfectly within nature's logic. For Feynman, the real beauty wasn't in having final answers. It was in discovering how much deeper the questions go. Why does antimatter exist? Because the equations allow it. Why does matter dominate? We don't fully know. And that gap between knowledge and mystery is where science lives. Standing on the edge of the unknown today, massive experiments attempt to recreate conditions similar to the early universe. Particle accelerators create antimatter routinely. Scientists measure tiny differences between matter and antimatter with incredible precision, searching for clues. Each experiment asks the same fundamental question: why is there something instead of nothing? Antimatter forces us to confront the possibility that existence itself emerged from a small imperfection, a tiny asymmetry written into the earliest moments of time. a cosmic imbalance that allowed reality to continue instead of canceling itself away. By now, antimatter no longer feels like just another scientific discovery. It feels like a crack in reality itself. A reminder that the universe is not built according to human intuition. Matter and antimatter are nearly identical. The laws governing them are almost perfectly symmetrical, and yet one dominates the universe while the other survives only in fleeting moments inside particle accelerators or cosmic rays. This final question haunted physicists like Richard Feynman. If matter and antimatter are equally valid expressions of nature, what makes our reality this version instead of another? The illusion of solid things in everyday life. Objects feel solid and permanent. A table is a table, a person is a person. Matter feels stable and continuous. But modern physics paints a very different picture. Atoms are mostly empty space. Electrons are not tiny balls orbiting a nucleus. They are probability distribution, regions where interactions are likely to occur. Particles constantly appear and disappear as energy fluctuations in underlying fields. Feynman emphasized that particles are not little objects traveling through space like miniature planets. They are events, interactions happening in space and time. Antimatter reinforces this idea in a profound way. If an antiparticle can be described mathematically as a particle moving backward in time, then the distinction between objects becomes less fundamental than the relationships between events. Reality becomes less like a collection of things and more like a network of processes. What we call matter may simply be a stable pattern within that network. Existence as a balance of possibilities. Quantum mechanics tells us that before an interaction occurs, multiple outcomes are possible. The universe doesn't choose a single path until interaction forces a result. Feynman's approach to quantum theory involves summing over all possible paths a particle could take. Every possible history contributes to the final outcome. This idea becomes deeply strange when applied to antimatter. If particles and antiparticles are two sides of the same mathematical description, then reality itself may emerge from a balance of possibilities rather than from fixed objects moving through time. In this view, existence is not a static state. It is an ongoing negotiation between possibilities allowed by physical law. Matter exists not because it was guaranteed, but because among all possibilities, this is the history that survived. The universe that almost wasn't considered again, the early universe. For a brief moment after the Big Bang, reality stood on a knife's edge. Matter and antimatter were nearly equal. Annihilation erased almost everything. Only a tiny excess remained. That means our universe is not the inevitable outcome of physics, at least not in any obvious sense. It is one outcome among many that could have occurred under the same laws, a slightly different imbalance. And galaxies might have formed differently, a perfectly balanced universe, and nothing complex would exist at all. This realization changes how we think about existence. The universe did not have to look this way, and antimatter reminds us of that lost alternative, a mirror universe that could have been. Feynman's lesson, comfort with uncertainty. Feynman's greatest contribution may not have been a specific equation or interpretation, but an attitude toward knowledge itself. He argued that uncertainty is not a weakness of science, it is its strength. Antimatter exists because the equations demanded it long before experiments confirmed it. Physicists trusted the mathematics even when it contradicted intuition, and when reality turned out stranger than expected, they adapted their understanding rather than forcing nature into familiar ideas. Feynman often said that nature's imagination is greater than ours. Antimatter proves this. It shows that reality includes possibilities we would never invent on our own. Particles identical to matter yet opposite in charge, capable of annihilating existence in flashes of pure energy, interpretable as motion through time itself. And still, it fits perfectly within the laws of physics. Identity in a quantum universe is another unsettling implication. If matter and antimatter are interchangeable descriptions within deeper equations, then identity itself becomes less absolute. The universe does not label particles as permanent individuals. Electrons are indistinguishable. Processes repeat without identity. At a fundamental level, reality may not consist of things, but of patterns that persist for a time. You too are a pattern, atoms arranged temporarily before dispersing again into the universe. Antimatter reminds us that what exists is not fixed. It is contingent, temporary, and deeply connected to the laws governing change. This idea can feel unsettling, but it is also profoundly beautiful. Because it means existence is dynamic. Why antimatter exists? Feynman's real answer, so why does antimatter exist at all? Feynman's answer in spirit is surprisingly simple because the laws of nature allow it. And once allowed, it becomes unavoidable. The equations describing reality contain symmetry. Antimatter is the natural consequence of that symmetry. The deeper mystery is not why antimatter exists, but why the universe ended up with enough imbalance for anything to remain. In this sense, antimatter is not an anomaly. It is evidence that the universe follows mathematical consistency even when it defies intuition. Reality is not designed around human expectations. We are the ones learning to adapt to reality. The final perspective, antimatter, forces us to confront a humbling possibility. The universe might not be fundamentally about matter or antimatter, or even time flowing forward. It may be about relationships, symmetries, and transformations, structures deeper than anything we directly perceive. Feynman once said that the joy of science is in discovering that things are not what they seem. Antimatter embodies that joy. It tells us that existence emerged from near cancellation, that time may not be as simple as it feels, and that reality is richer and stranger than common sense allows. And perhaps the most astonishing truth of all is this: the universe almost erased itself before it began. The fact that it didn't is the reason this question can even be asked.